All right, this is a continuation of my Calculus 1 using in the first and second derivatives lab. This is in your packet for your extreme values of functions, and this one kind of is a nice overview about using your first and second derivatives. So first of all, let's go through kind of what we're talking about. If I have a local min, so if I were going to draw a part of a local min, so here would be my local min of a function. It says f of p, or all your y values, the local min, the y value is less than all the values of f for points around it. So that's just what they use for the math terminology, if you will, that all the values around this point are greater than that actual value. That defines a local min. A local max is the opposite. The values of that point are greater than all the values around it. So just so you see that. Now, critical point is the x value or point, and I told everybody in class that I'm going to do critical point as an xy value, so I actually want to know the y value, and we know that f prime of p is 0, or f prime of p is undefined. Now, this is really important. We haven't done a lot of these, but a critical point can be where it's also undefined. We've done a lot with the zeros, but we will practice this more, I promise, okay? The critical value they call is the y value of the critical point. So these two, I just want to let you know, sometimes are interchangeable. The critical point really is an actual point xy. The critical value is just usually the x value. In this course, I will want the actual point. So I just wanted you to know sometimes there's a determination, there's a difference made between critical value and critical point. I remember once I was in college, my professor, I actually gave him the point. He says, I wanted the value, I only wanted the x value, and he kind of marked it wrong. I won't do that to you. I just want the whole point. Okay? So let's start here. Sketch the graph of a function with exactly two critical points, one of which is a local min, so I know all the values around it are greater. And the one is neither a local max nor a local min. Okay, so let's kind of sketch something. There could be quite a few that we can sketch. So I'm going to just sketch. There's my local min. Then I'm looking for something that is kind of neither. Okay, so here I'm going to call this my local min, my local minimum. Okay, and then this is a critical point because the slope is 0, but it's neither a min or a max. So this is a critical point. They both are. This is a critical point as well. So this is a critical point. That's a critical point. This one's an actual local minimum. This is a critical point that is not a local max or min. So when you draw a graph, you can have a critical point that, and we've seen it before, where the slopes are still all positive. So you're like, oh, that's still a critical point. The slope is still 0 there, but it's not a local max or min. All right, let's look at number 2. Sketch a graph which has exactly one critical point at x equals 2 and exactly one inflection point at x equals 4. So let's kind of do this. I'm going to do 1, 2, 3, 4. So this is my sketch. So I'm going to set that up. Now, an inflection point means the concavity is going to change. All right. So you don't want to, this one means the critical point could be a turning point, but where f prime of 2 is the slope is 0. That's what that's telling us. Here, the inflection point that I know f double prime of 4 is 0 as well, meaning there's a change in your concavity. So you can change from concave up to concave down or vice versa. All right, so let's kind of do a sketch here. So I'm just kind of making something up there. Slope is 0 for our critical point, and my inflection point, you know what I'm going to do? Let me go backwards a little bit. So let's try that again. I want to go a little higher so I can change in concavity. So this is up here, and they said the change in concavity was at 4. So let's look at here. So here's concave down. So first of all, here is my critical point. which looks like a local max, and then here it looks like it's concave down and switching to concave up right here. So I'm calling this my inflection point. And remember, your inflection point is where the concavity changes. So because this is like halfway between concave down and concave up, that's where I picked my inflection point. So this just kind of helps you with that. All right, let's try another one. For 3, it says indicate all critical points on this graph of f of x and determine which correspond to local max and which to local min and which to neither. So let's look at this. Right here, this looks like a critical point. This looks like a critical point. Because I'm looking at where all the slopes are 0. And this one looks like a critical point. So I'm trying to think where one would be neither. I don't really see one of those on this. So this one would be a local min. And this would be my local max because it's the maximum critical point that we have there. I don't really see on this graph where we would have one that's neither, but we will see on some. So there's that one. All right, so we're looking at where the slopes are 0. Let's look at this one. Now, this one's a little bit different. So this one right here, I looked at the actual graph of f of x. This is a graph of the derivative. All right, so I want you to think of this. You got to be careful. Sorry about that. This is the first derivative. It's almost like you have to think backwards. So here, all right, when we sketched our first derivative, right here, okay, are our critical points. Because remember, where f prime of x is equal to 0 are all our critical points of our original function. So right here, I have a critical point, and a critical point, because that's where I have there. So now I want to look at, all right, where's my local mins and my local maxes, because they want us to know. So you know what I did? It was I actually, just to help describe this to you, is I did my f prime bar, and we're going to go backwards to what is happening to my original function, all right? So right here, all right, are where it's 0, okay? So right here, this is above, okay? So the graph, this is above. So my slopes are positive. This means my original function of f, so this is what we're talking about down here, is increasing. Here, it's below, okay? So right here, it's below the graph. So if below, that means my slopes are negative. That means my original function is decreasing. Again, here, from here over to here, it's above. So it's above the graph. So that means all my slopes are positive, means my original function is increasing. And here is still above. So my original function is continuing to increase. But right here, we have a critical point. So let's talk about what is our local max and min. So if this is increasing, then decreasing, this is a critical point, and it's a local max, because it's increasing and decreasing on our original function, f. Here, I'm decreasing, then increasing, so this looks like our local min of our original function, f. Okay, I have to keep saying that. Here, I'm going to say this is neither a local max or min, because it's still continued to increase, but it's still a critical point nonetheless where the slope is 0. So that's how you can kind of tell. And this, I like doing this to try to think, okay, this is what my f prime bar is doing. This is what my graph is doing. Let's think backwards, if you will, and talk about what's happening to my original function. And then you can tell local maxes and mins from that. Okay, that's number 4. Let's try number 5. Indicate the graph of f prime of x as the x values that are inflection points. All right, so again, this is still my first derivative. Okay, remember, okay, that if we're talking about inflection points, that's when f double prime of x is equal to 0. All right. So if that's the case, that means your slopes of your f prime of x are 0. Okay. I'm just trying to get you to think this through. So basically, all the maxes and the mins of f prime of x are going to yield the inflection points of our original graph f. Okay, so if this is the first derivative, basically my inflection points are here, 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 and here. All right, that's where the slopes are 0 of this first derivative, which means that the change in concavity of our original function. Okay, so to find the inflection points, we must know where f prime of x is changing signs. So if you'll notice here, it's changing signs everywhere after that, and that's where your inflection points are. However, because f prime of x is the derivative of f double prime of x is a derivative of f prime of x, any point where f prime double prime of x changes sign will be a local max or min on the graph of f. So basically, if you were going to look at the original graph, right, where they cross the x-axis are their maxes and mins, but the max and mins of my first derivative graph are the inflection points of my original function where they're changing concavity. Okay, sometimes you have to think about that a little bit. So I just wanted to show that to you. We can talk a little bit more about that in class, but I wanted to show you that. The last one here is 6. It says indicate on the graph of the second derivative. Now this is the second derivative. Okay, this is a graph of the second derivative. You got to be careful what you're looking at. Okay. And this says indicate on the graph of the second derivative the x values that are inflection points of the graph of f. Okay, so if this is a second derivative, I know that f double prime of x equals 0 are my inflection points. So because that's the graph, I just see where it crosses the x-axis, and right here will be my inflection points. Because it's equal to 0. Okay, so let's write that down. The inflection points of f are the points where f double prime changes sign. So that means I shouldn't have put this one right here because this doesn't really change sign here. So the only two inflection points are these two. Sorry about that. Okay. So I hope that helps you looking at graphs and talking about first and second derivatives. Sometimes you have to watch this a couple times to get it in your brain, but this is in your packet, so look it over and we can talk about it in class.